So that what looks like a pulley really isn't a pulley in the sense of one that turns. It's a pulley in the sense of one that allows a thin wire to slide easily over it, supposedly with no friction. So we could just say there's no friction involved with that interaction. Yes. Did you use... So this situation, so this is a decent picture of the situation, and we have some things to account for. So for one, there is this height above ground that it has initially. This is 2 meters above ground. This other one, height 2 I'll call it, was 0.5 meter according to the problem. And given that one mass is larger than the other, we know that that larger mass is going to fall. And we'll end up having, in the final condition, a height 3. That's got to be 2.5 meters. 2 additional meters to the 0.5 meter that's off the ground. So this pretty much models the situation from a diagrammatic standpoint. We have a diagram of the situation. And so what we want to do now is begin setting up the energy balance. And so the way we're going to do that is we're going to start with energy pie charts for the initial and final state, and then move on from there. So what I want you to do now in the Socrative app is go ahead and answer that first question, and then we'll pick up from there. The initial energy state of the system. Energy has a number of definitions. One of them is the state or condition of one or more objects. And initially, the energy state of this system is each box, which is above ground, has its own gravitational potential energy due to the height above ground. Okay. Also know that in general, the potential due to gravity is always mgh. That's our general equation. So that'll become important later. So at the end of this game, there are 3 pieces in the energy budget. Okay, so I don't know if they're equal thirds, and we don't really care, because the purpose of the pie chart isn't for this to quantify the energy distribution in the final state. It's just to count. Okay, so if there's 3 parts, you make a thirds. If there's 2 parts, it's halves. So in the final state, we already worked out that there is some gravitational energy that object 2 has, so I could call that UG2. But there's a kinetic energy for object 1, that's the one that's impacting, and the other one's going up. It has kinetic energy. All right. So we have our initial and final energy pie charts, which we can, simply by using the equations, we know that kinetic energy is always half mv squared. We can literally build an equation where the sum of the initial stuff equals the sum of the final stuff, and that means if we have an equation that correctly matches the situation, then we can have a solution given enough information is input. Okay? So the trick now, though, is so this height here is associated with UG1. This height here is associated with UG2. But this height here, this is associated with UG2 in the final state. Now you could have called it UG3 if you wanted to. That would be perfectly fine as long as you know that UG3 is associated with mass 2. All right? I wouldn't do it that way, but you could, all right? It's perfectly fine. And then obviously the kinetic energy. So these are our general equations that match the kinds of energies that are being transferred. That's where the changes are. And remember, energy, it's a lot of things. It's one way to describe an interaction. It's an accounting system for those interactions. And remember, it is a way to account for changes in position and speed. So kinetic energy is that changing speed thing. Potential energies, but whether it's spring or gravity, you name it, it's based on a position. Changing positions mean changing speeds. They're always together. All right. One thing to take note of is it is the case that this object, will be moving down with some speed v, and this object will be moving up necessarily with that same speed v. You could bother with v1 and v2 trying to keep track of individual speeds like you were for mass 1 and mass 2 or height 1 and height 2, etc., but realize these two blocks necessarily have the same speed because they're attached to the same wire. They're in different directions, but speed is directionless. Okay, so keep that in mind as you set up your balance. So really all you have to do now, the sum of initial energies, which you have the equation, and all you got to do is subscript its parts properly, has to equal the sum of final energies. And you sum those up as well using the correct subscript. So take 5 minutes here to set up your energy balance and solve for the impact speed in there. So work on that individually, and let's see what happens. So hopefully you wrote an initial, your energy balance should have been something M1 G1 H1 plus M2 GH2, and that would equal M2 GH3 plus half M1 V squared plus half M2 V squared. So if you didn't get 2.8, could be because you didn't have the right energy balance to begin with, but hopefully you can see that you know, this right here, okay, and that, kinetic energy here, kinetic energy there, just dropping right out of the pie charts using the standard equation and just inserting the right subscripts, which therefore lets you insert the right quantities, values, and you solve from there. So continuing on with that, you could bring the potential energy term from the final state leaving just kinetic energy on that side, and your V squared would work out to be, well, let's do this. Instead of that, a G comes out, bring it, multiply by 2 both sides, M1H1 and then in the final analysis you get 2G plug all those numbers in, you get about 2.8 meters per second. So one of the things that's easy to mess up is this H3, if you remember, was an additional 2 meters to the half meter it started, because the following one only goes 2 meters, which necessarily adds to the other side since it's one string. The 3 is not associated with the 3 meters that the cylinder is above ground is not associated with anything. It's not associated with the energy transfers. Just a mechanism that lets the string move. Okay? So keeps the system coupled, if you will, in that regard. So in problem number 3, you're driving your car uphill along a straight road. Suddenly you see a car run a red light and you slam on your brakes. So we are going to take that chunk of the hill out. All right, so technically, the hill, so right here, we start the skid, and then we could say up here at the top of the hill, or the top of the hill as far as we're concerned, and this is where we stop the skid. So we have this hill, and apparently the skid marks, that sounds so nasty. I'm not recording this, am I? Oops. All right. So there is a distance of 100 feet, which if you were to just Google and type 100 feet to, you'd get that it equals 30.48 meters. We need things to be metric. Okay. And so it's a 10% grade on the hill. So we're going to, while it's the case that, the car was moving with some speed, okay, so there was a speed that the car was going that was not equal to 0, and then up here, speed equals 0. So we go from a non-zero speed to a 0 speed. That should tell you something about energy. And we know that there was friction along this ramp, and this uphill screech to a stop situation, so we could just pick any spot really. Okay, and we know that there is a force of friction acting opposite of motion. We know that the car has a mass that points straight down, even though the surface has a reaction that points straight up. Okay, so these forces, normal force perpendicular to the surface, well, that means that there's a portion of that weight force that's acting down, and there's necessarily a portion of that weight that's accelerating up the hill or decelerating up the hill. Okay, so if you remember back to our inclined plane setup and how we worked out the forces there, and the thing to note is that this angle between the true weight vector and the apparent weight along the ramp, remember, we tilt our xy axis so that the x-axis is parallel with the ramp and the y-axis is perpendicular to it along the normal force axis. Okay? And hopefully you remember that since this portion of the weight that's parallel to the ramp, since it's opposite the angle, that's a sine theta, and this portion of the weight that's adjacent to the angle has to be a cosine theta. All right? So we know that our normal force, we forgot something here. It's moving up, right? its gravitational potential energy is changing. So that means I need to say something about the height, which wasn't given to me, except for the fact that trigonometry says, since the length of the ramp and the height of that ramp are related by the sine function, I can describe the height change of the vehicle along, relative to the skid length, and determine how high the car went with respect to gravity. All right? So this mg cosine theta is equal to the normal force. Does anybody remember why? Is there any acceleration in the y-axis? Meaning along the direction that the normal force acts? No. So that means those forces are equal and opposite. And so here's the thing about friction. Friction always involves a normal force. The normal force is always mg cosine theta. The difference is that when everything's flat, cosine theta is 1. Bullet point. The normal force is always mg cosine theta, ramp or not. And not on a ramp, cosine is going to, of 0 is 1. Otherwise, if the angle isn't 0, then it's going to be non-zero. It'll be some fraction of that weight, small or large. All right? So that is the setup that accounts for lengths and masses and force interactions. And here's the thing with energy. Half of the energy puzzle is how forces do work. Gravitational forces, spring forces, friction forces, they do work. Then the energy, the kinetic energy, changes in accordance with those other works. Either adds to the kinetic energy or takes away from it, one or the other. Right? So that's the setup. And so the math is easy if you set it up right. All right? So now that we're in that boat, now we can take some time here and start to do the energy pie chart so we can set up the energy balance and compute. Basically, what was the actual speed that this motor is started at so that you can know whether or not traffic court is worth it. All right? So initially, all you have is kinetic energy. The car enters the skid zone at a speed. In the final condition, we experienced a change in gravitational potential energy. That and friction worked to bring the car to a stop. In fact, it would be good to actually call this the work done by gravity. Still the same equation, mgh. Because gravity is wanting to push it down the hill, and friction is wanting to make it stop going up the hill, to make it personal. Gravity and friction are party poopers, all right? So again, this is one of those subtleties. The moment it comes to a stop is the moment that the work by friction is done. At least the work by kinetic friction. All right? So at that moment, static friction is what's keeping it from rolling back down the hill. Okay? Or the brakes being on or something like that. Okay? So all of that kinetic goes into work done by gravity and friction. Okay? So now one of the reasons why there's no potential at the beginning is that we are defining this implicitly demands a 0 spot. Up here, you're at H, not equal to 0, which implies that down here, H is equal to 0. That may not be obvious, because with respect to the Earth itself, that's not the 0 point. But we don't care about that, to be quite honestly. We want a 0 point that's relative to the region where the work was done. So it's about the change in potential energy. This change in potential energy was associated with this work. So my 0 point can be anywhere I want it to be, and it needs to be where the initial and final state. It needs to be either at the initial state or the final state. It just has to be one of them. Math will work out either way. Usually it's the initial state. Okay, so that's the full setup of the force interactions and then how the energy distribution lies between initial and final states. Which means, okay, of course we know that kinetic energy is 1/2 mv squared. We know work done by gravity is mgh, and work done by friction will be force times distance, which we called it d here, the friction force. Work is always a force times distance. In fact, this right here, that's a weight force. mg is a weight force. All right. So you should start with something like 1/2 mv squared. It's going to be the sum of these two things. That's how it all starts. And take note of the fact that H is defined that way. Recall that friction is mu n. So this problem, you go from 1/2 mv squared in the initial state. mgd sine theta is the gravitational part. Mu mg cosine theta is the friction part. Nice thing is we don't have to bother with converting the mass of the car because it drops out of everything. And so your V is just going to be 2GD, which is the only common part, times sine theta plus mu cosine theta. And if you remember back to our force friction analysis, that sine theta plus mu cosine theta keeps showing up in the friction game. It's always the fraction of acceleration along the inclined plane. All right? So you should get, you plug in the numbers and you will get the right answer from that. If you plug and chug all of that stuff in there, you should get, I think it was 21 meters per second. Which was roughly 48 miles per hour. So don't bother going to traffic court. All right? So that's, okay. So given those features, which I hadn't pressed the record button, so Whoever watches this later has to catch up really fast in the doing of it. This is the ski problem. All right, so fill in your initial and final states and then set up your energy balance, knowing that these are the energies involved. It's just where are they involved? Okay? How do they distribute? They show up in two places, one place, etc., etc. So, okay, so the way that this breaks up, these two pie charts break up in this fashion. You have work done by gravity at the top, and you have some initial kinetic energy at the top. This is the ski jump problem, because the skier starts off at 2 meters per second. At the end of the ramp, you have a whole bunch of work done by friction that was in a very small way impeding the increase in speed. And then there's a final kinetic energy. So from that, we can write an energy balance between initial and final that is literally just an mgh plus a half mv squared plus a mu nl plus another half mv squared. And so I'm going to go on to a new screen here. So let's go to the balance writing part of this deal. So in the initial side of things, we had a mass, gravity, height, basically involving the height of the ramp. We had some initial kinetic energy, since we'll use a V naught for initial speed. Then at the end of the ramp, there was a whole bunch of work done by friction. So mu n is the frictional force. In fact, let me just write little f for friction times the length of the ramp. That's force times distance. It's work done by friction, plus the final kinetic energy. So we'll just use V squared instead of V naught. So we have our energy balance in general terms. Now we're going to make it specific to our situation. And you might recall that the height of the ramp can be related to the length of the ramp and the angle, sine theta. mv naught squared isn't going to change, but friction, we know it's mu n, okay, which is going to be the normal force, and in this case, the normal force is a fraction of the weight. That's what the cosine does. So the things to remember would be this thing right here. This is the normal force. Okay? And friction equals the coefficient of friction times the normal force. And on an inclined plane, it's always a fraction of the normal force, and it's the cosine fraction of the normal force. All right? So, oh, and we're missing the L. I left the L out. Sorry about that. Now, that means we can pull things to, well, first, we should just note that mass is common to every term. So I don't need to even bother with the mass, which is great because we weren't given the mass of the skier. Because the mass of the skier isn't going to matter. The change in kinetic energy is going to be what it is due to friction and gravity. So now we can GL sine theta minus mu G L cosine theta equals half mv squared minus half mv naught squared. So now the physics was done at the top of the page, okay? And now we're in math land. just an algebra problem. So we can pull length out, since that's part of what we surely want to know, okay? And that will be a G, actually we can pull LG out. Over here. And we'll have a sine theta minus mu cosine theta equals 1/2 mass v squared minus v naught squared. So in the end, L, something that we need to know, will be, oh, I brought mass back in after I took it out. Excuse me. You guys got to keep me honest here. Just have a habit of putting that M next to my v squareds all the time. All right, so difference of speed squared over 2g times this trig business. All right. So if you convert 80 kilometers per hour to meters per second, you get 22.2 meters per second. You can just do that in a Google search line. 80 kph2, probably tell you it before you hit enter, what the answer is. So if we put the data in from this problem, we will get a length of 61.9, or is it 7 rather, 7 meters. And this implies, if you do that times the sine of 25 degrees, that the height of this ramp is 26.1 meters. So didn't have room to write it in there, but just a plug and chug experience. All right, and that's reasonable. 60-yard ramp, basically. That's how, a little over half a football field, but only a fourth of a football field high, 25 yards roughly. That makes sense. If it was 250 meters, it's like, wow, this person's going to be going half the speed of light by the time, whatever. Probably not that fast. So, not a bad way to get what we need. So all this stuff goes into the design. Okay, so we want the skier, we want everybody to leave the ramp, to have the opportunity to leave the ramp at the same speed. All things being equal, if everybody has the opportunity, if they have good form, et cetera, then they'll attain a maximum energy at the bottom of the ramp. And then if they continue with their good form, flying the right way, because you need to, I think, spread your skis out and lay at a particular angle so that you minimize your air, or maximize, so you lift longer. And so the more lift you can have, the longer you fly, the longer your distance, da-da-da-da. So if you design a ramp that gives everybody the opportunity to leave with the same maximum, then it's a test of not only their form that got them to the maximum, but a test of did their form persist. Because the best form will always lead to the best distance. So it's a great test if you design the ramp well. Okay? And you want to design the ramp with safety in mind. Okay, so if they're leaving the ramp at 200 kilometers an hour, this is probably not good. Okay, because if they don't land perfectly, they're going to roll and break things. But at least leaving at 80 kilometers per hour, they'll slow down in the air and land at a speed that's reasonable to manage. Okay, so lots of things go into the design, and one of them is somebody doing the physics. And this would apply to any area. This would apply to biomedical applications, for prosthetics. We're starting to do all sorts of lab-on-a-chip stuff that we inject into people. You name it. all of those things, safety, interaction with biomaterials, the list goes on. And so physicists and chemists and biochemists and all pile in on those kinds of problems and contribute their part to the constraints and the optimal setting. And so a biochemist would do an energy balance like this, except they would be talking about Gibbs free energy and enthalpy and things like that. Chemists and biochemists and molecular biologists would deal with those sorts of things. But their energies would still be a sum of energies in and out. It would just be different energies, different formula, measuring different things than distance, length, etc., speed. All right, so the ideas will be the same out there, even if you don't end up doing a physics energy balance. An energy balance is an energy balance. All right.